Okay, here's the topic of our video, intermolecular force types. There's going to be 4 of them. Here's some useful information if you need it. Here's our objective. We want to see what they have in common, what makes them different, compare and contrast. So if you were comparing these two, you would know that one's got a permanent dipole and the other one does not. That's the goal. In general, an intermolecular force is between two molecules. It's an attractive force between two molecules. We're just going to go over the types and how to draw them. The first is a dispersion force. Dispersion force has like an area of high density of electron creating a partial negative and an area of that is not, and then they form an attractive force. The dotted lines mean an attractive force. This intermolecular force exists in any molecule, anything that's got electrons, it could happen. The next is hydrogen bonding, most famous with water. This is when you've got hydrogen bonded to a fun element, fluorine, nitrogen, or oxygen, fun, F-O-N. You create these dipoles, and then they line up, and you create attractive force, all right, between them when the opposite dipoles align. A dipole to dipole is essentially the same thing as what we just saw, but you don't have hydrogen bonded to the fun element. You have other dipoles, like chlorine to carbon or fluorine to carbon. You have your dipoles and they align, and then you create an attractive force. This is in polar molecules. The fourth one is ion to dipole. This is when you dissolve something in water or a polar solvent, and the solvent surrounds the cation or the anion, and there's a bond that forms as a result. And here they are all together. Now, dispersion forces, are they in this molecule, acetone? The answer would be yes, because acetone's got an electron. Are they in this? Even though the things are aligned, this is like hydrogen fluoride, even though they're aligned negative, negative, in terms of the dipoles, it would still have a dispersion force. Nitrogen, yep. How about this hydrocarbon, yep. And they'd be all throughout this person. Anything that's got an electron would have dispersion forces. Hydrogen bonding, water, it's got lots of it because you got H bonded to O. Hydrofluoric acid would also exhibit hydrogen bonding. This one, it would exhibit it because of the amine. The blue atom there at the end of the molecules is bonded to a hydrogen, creating hydrogen bonding. This is ethyl alcohol. It too, this is red is usually oxygen. It would have hydrogen bonding when they align like this. In cellulose in plants, there's hydrogen bonding between the water and the oxygen there, and that allows water to move up to the canopy of trees. Dipole, dipole. This is when you've got a polar bond that's not hydrogen to a fun element. Here you can see it between this carbon and oxygen. Here it's between chlorine and carbon. Here it's oxygen to carbon again, and then we've got oxygen to carbon again. These are all dipoles, just different ones than the ones that are particular to hydrogen bonding. Ion to dipole, any salt, sodium chloride, sodium fluoride, sodium iodide. The cation gets surrounded, or this is the anion, gets surrounded by the water, and the reason I know it, it's the hydrogen end of the water, so it must be the negative. And this is the anion being surrounded by the water. All right, that's the ion dipole bond. And remember, it goes for any solution. Pretty much most solutions where you've got a solute, a salt. Some solutions are not, like if you've dissolved two liquids like ethyl alcohol and water. That's not an ion to dipole, but typically most salts are this. All right, now what do they all have in common? You've got two molecules, two spheres that are being attracted to each other. It's usually an attractive force. All right. It's going to involve dipoles. Different types of dipoles are in each one, but they all basically involve dipoles. And you're going to show these dipoles with those deltas. All right. These forces will affect physical properties. In general, the stronger they are, the higher the boiling point, the higher the melting point, the higher the viscosity. The first one was dispersion. That's the one formed by the random movement of electrons. Has momentary dipoles, meaning like they come and go. These are generally considered the weakest of them. All right. It says they exist because species are polarizable, meaning you can make these areas of negative or positive that can come and go and change in spots in its location. And they're, for all molecules, they exist. Right? Hydrogen bonding, that's a particular dipole. It's when you've got H to a fun element. These tend to be stronger than dispersion, and they tend to be stronger than dipole-dipole. This is something like a polar bond other than those three that are unique to hydrogen bonding. They tend to be a little bit weaker than hydrogen bonding, but stronger than dispersion forces in general. It's not a golden rule. Now these two, the dipole-dipole and the hydrogen bondings, are made from a permanent dipole, meaning it's always there, meaning the species is polarized in terms of the bond already because of an electronegativity difference. Ion to dipole is when you dissolve something in a solute. And this is a really strong intermolecular force. All right, here are my sources. Thank you very much. I hope you have, let me know if that helps and ask me any questions if you got any.